Molecular orbital theory. Molecular orbital (MO) theory is a model used in chemistry to describe the behavior and properties of molecules based on the principles of quantum mechanics. It provides a detailed understanding of chemical bonding by considering the interactions between the atomic orbitals of individual atoms to form molecular orbitals. Here are some key points about molecular orbital theory. Atomic orbitals. Atomic orbitals are the regions around an atomic nucleus where electrons are most likely to be found. In molecular orbital theory, these atomic orbitals combine to form molecular orbitals. Molecular orbitals. Molecular orbitals are wave functions that describe the behavior of electrons in a molecule. They are formed by combining atomic orbitals in a linear combination, resulting in a set of bonding and antibonding molecular orbitals. Bonding molecular orbitals. Bonding molecular orbitals, BMOs, result from constructive interference of atomic orbitals. Electrons in bonding orbitals stabilize the molecule and contribute to chemical bonding. The energy of BMOs is lower than that of the original atomic orbitals. Antibonding molecular orbitals. Antibonding molecular orbitals, ABMOs, result from destructive interference of atomic orbitals. Electrons in antibonding orbitals destabilize the molecule and weaken chemical bonding. The energy of ABMOs is higher than that of the original atomic orbitals. Sigma, sigma, and pi, pi, bonds. Sigma, sigma, bonds result from the overlap of atomic orbitals along the internuclear axis, while pi, pi, bonds result from the overlap of atomic orbitals above and below the internuclear axis. Sigma bonds are usually stronger than pi bonds. Filling of molecular orbitals. Electrons fill molecular orbitals in a way that follows the Aufbau principle, Hund's rule, and the Pauli exclusion principle, similar to how electrons fill atomic orbitals. The molecular orbital energy diagram helps determine the electron configuration of a molecule. Bond order. Bond order is a measure of the strength and stability of a covalent bond. It is determined by subtracting the number of electrons in antibonding orbitals from the number of electrons in bonding orbitals and dividing the result by 2. A higher bond order indicates a stronger bond. Molecular orbital diagrams. Molecular orbital diagrams are used to illustrate the formation of molecular orbitals and the electron configuration of a molecule. The diagram shows the relative energy levels of the molecular orbitals and the electron occupancy. Molecular orbital theory applications. Molecular orbital theory provides a fundamental understanding of chemical bonding in molecules, explaining properties such as bond length, bond energy, and magnetic behavior. It is used to analyze and predict the stability, reactivity, and spectroscopic properties of molecules. Linear combination of atomic orbitals, LCAO. In molecular orbital theory, atomic orbitals combine to form molecular orbitals through a process known as linear combination of atomic orbitals, LCAO. This involves adding or subtracting atomic orbitals to generate bonding and antibonding molecular orbitals. The combination is determined by the relative phase and energy of the atomic orbitals. Symmetry and molecular orbitals. The symmetry of molecular orbitals plays a crucial role in determining their bonding properties. Symmetry considerations help determine which atomic orbitals can combine to form bonding or antibonding molecular orbitals. By applying group theory principles, one can predict the symmetry of molecular orbitals and understand the overall symmetry of a molecule. Homonuclear diatomic molecules. Homonuclear diatomic molecules, such as H2, N2, and O2, provide a good starting point to understand molecular orbital theory. For example, in the case of the hydrogen molecule, H2, the one's atomic orbitals of 2 hydrogen atoms combine to form a bonding molecular orbital, sigma 1s, and an antibonding molecular orbital, sigma asterisk 1s. Molecular orbital energy levels. In a molecular orbital diagram, the energy levels of the molecular orbitals are plotted along the y-axis. The bonding molecular orbitals are usually lower in energy than the atomic orbitals from which they are formed, while the antibonding molecular orbitals are higher in energy. The relative energies of molecular orbitals determine the stability and reactivity of the molecule. Bonding and antibonding interactions. When atomic orbitals combine to form molecular orbitals, bonding occurs through the constructive interference of the wave functions. Electrons occupying bonding molecular orbitals stabilize the molecule by sharing the electron density between the atoms. In contrast, antibonding molecular orbitals result from destructive interference, leading to regions of electron density with opposite phases. Electrons in antibonding orbitals weaken the chemical bond. Overall, molecular orbital theory is a powerful tool for understanding the nature of chemical bonding and the properties of molecules. It allows chemists to explain and predict the behavior of various compounds and facilitates the design and synthesis of new materials with desired properties.